the topic of privacy. In this case, we don't necessarily define a minimax game, but we do have the concept of a defender and an attacker. Specifically, say that we have a lot of training data that only the defender has access to. And we use that training data to learn parameters that we then want to publish. Maybe we want to train a medical diagnosis system on sensitive private medical records. And then we want to open source our model so that doctors around the world can use it to diagnose their patients. If we then publish these parameters, they're available to attackers who can see public data. And these attackers might try to reverse engineer our training set and recover private medical information. All right, so one of the best situations in adversarial machine learning is actually the privacy of training data problem. This is one of the very few cases where we actually have provable guarantees, and things are actually easier for the defender than for the attacker. The provable defenses that we have are based on a framework called differential privacy. If you're like me and you've been working in deep learning for years and working with calculus quite a lot for training deep models, you probably hear the word differential and immediately think of derivatives. But here, differential is actually referring to the difference between two different data sets. If we imagine that there's one data set containing a specific person's records and another data set lacking that person's records, differential privacy says it would be great if we could train our algorithm on these two different data sets and end up with parameters that are statistically indistinguishable so that no attacker can tell which of the two training sets the parameters came from. Being able to do this requires introducing some stochasticity into our training algorithm so that there's uncertainty about which parameters come from which data set. And if we can show that the stochasticity has a greater effect than the inclusion or exclusion of an individual patient, and the attacker can't figure out whether that user was even in the training set or not, then in some sense we can say that we have not violated that patient's privacy because they didn't substantially affect the final parameters. One of the techniques that we developed at Google is called private aggregation of teacher ensembles. The basic idea is to partition the data into different subsets and train a different teacher network to model each of these subsets of the training data. Because no individual example appears in more than one of these subsets, each teacher network is learning completely independently how to solve the problem. We then have the teachers vote about how to process new public data, and we use noisy votes to determine the final output for each input example. If two teachers agree on how to process an input example, it must be because of a general pattern and not because of a quirk of one user's data. Because the two teachers voting did not ever both see the same user's data. The main reason we need to add noise in the aggregation mechanism is that there's still one way we could leak private information. Suppose that the teachers don't actually agree. If we then refuse to publish any classification for the input data, an attacker could learn something about the fact that the two teachers did not agree. What we do instead is we have lots of teachers, and we throw in noisy votes as well. This way we can always publish a prediction, but sometimes that prediction will be wrong if not enough teachers agree on the right answer. Using the noise and using the framework of differential privacy, we're able to prove that this is actually a secure mechanism for publishing classifications. And we can actually provide explicit quantitative bounds on how much privacy is being lost.